Well, I guess we got some homework to cover, eh? This stuff's due Monday. So this is the Q equals VA stuff, chapter 9. So what you got here is you just got two basic equations that you could use. You got Q equals VA, and then commonly you might want to find the velocity. To do that, you take Q over A. Okay. So you could use either version of it, depending on what you want. So, to me, it seems to be pretty straight up stuff. You just find the area and then multiply it by the velocity to get the flow rate. And then you can divide the flow rate by the area to get the velocity. And that's really about it. I don't know, are there any questions on any of this stuff? So what you're after is the cross-sectional area. So that's 4 feet by 6. Okay. So if you want the velocity in this channel here, you take the flow rate, 32. Now what CFS is cubic feet per second. And then you divide that by 24 square feet. So what happens here with the units is the square feet cancels out all but one of the cubic feet. And then when you divide 24 into 32, you get 1.33. And then what's left for units is feet per second, which is a velocity. Y'all okay with that? All right, this next one here, you want to find the velocity in the pipe. Now, the one thing on this is there's these different units that are used for measuring flow rate. And what they are, they're typically abbreviated with 3 letters. GPM means gallons. That's the G. P means per. Now, whenever I see the word per, I always think of dividing. And then M means minutes. Okay? So that's gallons per minute. And that's used a lot for flow rates in pipes. Now, quite often what we want to do is get that into cubic feet per second, which is actually more commonly used in channels, things like that, rivers and channels. So they're both measuring a flow rate, a volume, and a time, but they're just different units, okay? So this is commonly used in pipes here. And this is commonly used. This is, the abbreviation for this one is CFS, cubic feet. They don't use a per on that, they ask me seconds, so they'll call that CFS sometimes. Okay, and so they use GPM for pipes, and they use cubic feet per second for channels, and for rivers and stuff like that. Okay. And then what's the other flow rate number in the water industry? It's 3 letters. Yeah, MGD, which is, now this is for plants and stuff. So what that is million gallons, because water plants have a lot of flow. The D is day. So this is for plants. So by that I mean a water plant or a wastewater plant or something like that, okay? So those are the different flow rates. So you got to be able to convert between them. If you want to get a velocity, you want to be in cubic feet per second. But the MGD, it's just a common abbreviation for water plants. You know, what the deal is with that is it's just makes the numbers more manageable. I don't know, anybody know what the Albany plant is? Is it 20 or 30 or something?
Its capacity or?
About what it normally does in a day, or capacity, whatever.
I want to say Troy said like maybe 30.
Okay, yeah.
The wastewater plant. I don't know about the water plant.
Okay, yeah, 30 is kind of, I remember 20 to 30 somewhere in there. So, you know, so they can talk about those as round numbers. All right, so what you got here is you got 36 gallons per minute. Now, if you want to find a velocity, you've got to get that into cubic feet per second. So, of course, a minute is 60 seconds. Now, I've got the units going there, so the minutes on the top and the minutes on the bottom cancel, so that gets me gallons per second when I divide that by 60. But then I need to know, what is it, 7.48 gallons in a cubic foot? Okay. So you do that conversion on this problem to get that into cubic feet per second. It's about 0.0802. So that's the flow rate in cubic feet per second, okay? There you go. So we all right with that? Then do the rest of it, okay? Now this next one is a little bit of work getting through it. You know, there could be a lot of things to keep straight on these. So what I like to do whenever I see something like this, where I've got different diameters or flow rates, I'll just calculate the area first, okay? So the diameter of this thing would be 3 inches over 12. That's inches per foot, okay? So the diameter of this thing is what you would want first. And you got to think ahead on these things, and so you want to get that in feet. So that's 0.25 feet, okay? So the radius is 0.25 feet over 2, so that's 0.125 feet. And then the area is pi times the 0.125 feet squared. So that'll get you A1, and that's 0.0491. And then you can do a similar thing. Actually, we call that A sub A, I guess. There we go. Now, you can do a similar calculation there and get A sub B, 0.005454 square feet, okay? All right, and then you've got the velocity coming in, so you can find the flow rate at A, which would be VAAA, and when you do that, you'd get 0.1782, and that'll come out to be cubic feet per second. Okay. And then you can find the velocity at B, which is what you want, and that will get you, to get that, you get Q over A sub B. Now notice that the flow rate at A is what you're pushing through that pipe system, so that's also the flow rate at B, and you can just call it Q. That's the flow rate through the system. What you push into one side of that piping system is what's going to flow through at A and B and everywhere else. So Q is just Q. And so you can take Q and divide it by A, and what you get there is 32.7 feet per second. Okay. Now you could do this faster if you wanted. This is kind of the standard way to do it, using the standard formulas on your formula sheet. You could also, if you remember this is take 3.631 feet per second and then multiply it by the ratio of either the diameter or the radii squared. So basically you're going to multiply that by 9. And that'll get you the 32.7 also, a lot quicker. So that's another way to do it. Okay. You got any questions on that? Or any other questions on the homework there? So what we've been doing here is this Bernoulli's equation, which is just an energy equation using tables, is how I think about it. So remember, everything you put on the table would be in feet. Okay? So everything on that table is in feet. So you got to convert to feet before you put it on the table. And when you take it off the table, you've got to convert it into some other unit that you're going to use. Okay? So just remember that table, everything on the table has to be in feet. That way you can add things together. Okay, that's the idea. So why don't we have a look at this one? This is kind of similar to what we were just looking at. 106. So I've got a little table down there that we could fill in. We just got to do a bit of work before we can fill that in down at the bottom there. So how about starting off with 12 psi? How many feet of energy is 12 psi? So you get to put that up here. It's a little tight fitting everything on there, but get 12 psi converted into feet.
27 feet.
That sounds about right. Yeah, 27.7. Yeah. So yeah, just get that converted. So 12 psi. And just remember the proper conversion to use on these things. That you got things on the proper side of the fraction and all that. Remember what 12 psi is 1 over 1. So the psi will go on the bottom. So what you got here is 1 psi will get you 2.31 feet. So that's going to come out to be 27.7. I took this out of this because these numbers get a little fine. So I made it 7 too. It might be overkill, but I guess you can, can't hurt. Okay. All right, now what we're going to do is we're going to take, this is a chemical feed pump. It's called a Venturi. It's a device where the pipe necks down to a smaller diameter. And let's see what the effects of doing that are on the pressure. So we're going to take it down from a 1-inch diameter to a 1/4-inch diameter. And what we want to do is to analyze this, we want to find the pressure at B. So we are going to have to concern ourselves with velocity on this. So how about getting the 7 gallons per minute into cubic feet per second? So why don't you do that conversion there? It'll be a small number. Less than that, at 0.0156. So yeah, you got to divide it twice to get it in, you're looking for 0.0156. So you know if you got questions. So I like to, do the conversion step by step. The other day, someone was saying, "Well, you're an engineer, right? So you kind of skip through this stuff kind of fast, right?" And because you're good at math or whatever. And I said, "No, I take my time on these. When I'm doing actual engineering stuff, I set everything up carefully, and I do all this stuff because I don't want to make a mistake. See, so that's why I put all these units in here and show everything and all that, because it just cuts down on the errors." I tell the engineering students that if you make a mistake in school, you get a little red mark on your paper, but if you make a mistake out there when you're working, it can have lead to a lot more problems, I've had all sorts of things happen when I was working. That could have caused problems had they not been caught. The company I worked for had a little dispute because they staked out a bridge footing about a foot too high. Something got screwed up in there. Luckily, the contractor didn't start building the thing, but man, that would have been a mess because what those relationships always turn out to is you'll figure it out sooner or later, and when you do, you got to fix it, and that would have been a lot of money. So luckily they caught it before anything happened, but anyway, that was just things like that can really cause some problems. Okay, so what we do there, we take 7, divide it by 7.48, divide it by 60, and I came out with 0.0156. I always think of you all too in water, if miscalculating a dosage or something, that wouldn't be good. Okay, so you want to be sure you're getting that stuff right. Okay, so that gets us the flow rate going through the system, 0.0156. All right, so how about the radius of A in feet then? It's got a 1-inch diameter, so that's a 1/2 inch radius, but then you want to get that into feet because we're working with cubic feet per second, so we want to get everything in feet. Units should match when you're doing these formulas. I got about 0.0417 or something like that. Once you got the radius there, 0.0147, you can calculate the area once you got that, pi r squared. So the radius is 1/2 inch, a foot to 12 inches. So that's whatever the heck it is, 0.0417. That's square feet, and then do pi r squared on that, and you'll come up with the area. And that's in square feet. It's 0.005454. Whoops, I put the square on the wrong side of that, didn't I? There we go. And then take Q over A. You got the flow rate, and you got the area, and you'll get the velocity at A. We got 2.86. And then you could square that and divide it by 64.4, and you'll get velocity head, which is what goes into the chart. Now, that isn't going to be a whole lot, but let's put it in there anyways. I just take it out to the 100th. And like I say, it's not very big. 0.13 feet. And you can see why people often ignore velocity head. You know, 2.86 feet per second is a pretty good flow, right? Pretty good speed, but it doesn't get you much velocity head at all. It's just 0.13. All right. So that's the deal with that at A. We good with that? 0.13? All right. Okay. Now, I guess we can fill out the chart there at the bottom now, at least on the left for A. We don't get any elevation, it's just horizontal. It's not going up or down or anything, so we don't need to worry about that. And up above we got the pressure head, and we just found the velocity head. So I think we got 27.85 feet of energy. Okay, that's what we got at A. And we're going to assume no head losses. So that's what we got to work with at B. Okay. And the units on this thing are feet. Okay. Okay. So why don't we do that all over again for B this time? Find the radius, find the area, take the flow rate and divide it by the area and find the velocity. It's going to be pretty high this time because what we're doing, we're taking that big, well, not big, but that 1 inch diameter pipe and we're necking it down to a 1/4 inch. So that speed's going to go up considerably to get it through that little opening. And let's see, so the point of doing all this stuff is to see what the effects are on the pressure at B. Thirty-two and a half or so. So it's the velocity head went way up. And see, that's the purpose of a venturi, is to do that. That's the intent. Okay. So why don't you solve for the pressure head and see what you get. Because we know the velocity head's about 32.52 feet. So what you all coming up with? It might be kind of an odd answer, but it's what it is. So what do you got?
Negative 1.35.
Yeah, right. It's a negative number. Okay. I got 4.67 is what I got negative. So what does that mean? What's happening in that little narrow orifice? What's going on? Yeah, creating a vacuum, okay? And see, that's the whole purpose of this thing, because it's a chemical feed. So you create a vacuum in that narrow orifice. Well, it isn't quite the right word, but it pulls the chemicals into that flow, okay? And that's what you want it to do. That's a chemical feed. Two places I've seen this commonly used are, one is to pull something in, like a chemical feed. And the other thing I've seen it used to do is to evaporate something, because in a vacuum you can evaporate fluids more easily. So, they use these on carburetor jets. And I don't know, I imagine fuel injection has something going on like this. Of course, I took apart my carburetor a long time ago, but I wouldn't take apart my fuel injection. I don't think I'd get into that, but probably got something like that in there. Okay. All right, so what you've got here, you've got negative 4.67 feet, and you can convert that into pressure and see kind of what the results of that will be. So negative 4.67 feet, 0.433 psi per foot, and you'll get the pressure, and it's just a little bit more than 2 psi, but it's negative, okay? So if your chemicals have a higher pressure, they'll be pushed in. Okay? And that's the whole intent of that device. So we okay with that? A lot of messing around with that, but you can kind of see the results of that, okay? Let's see. Okay. So we're good? Good with that? Okay, so this velocity thing, it's a lot of work to calculate it, obviously. Let's just say we've got, I don't care, 8-inch pipe. I want to show you a little trick here. 8-inch pipe. And let's say we've got 900 gallons per minute flowing through it. What's the velocity? And I just made this up kind of randomly. I can tell you right now it's 5.74 feet per second. Now here's the trick. Look on page 108.
Chart.
Yeah, there's a chart, okay? And that's a good one, okay? So that's actually, that has head loss calculated on it too, but another nice little feature of that is it's got velocity. So if you've got even sized pipe that's normally manufactured, that starts at 2, 3, 4, then it's evens after that, 6, 8, 10, 12, 14, 16, and 18. Those are common pipes that you might run into. They're right on there, okay? And it's just Q over A is all it is. So if that assumes that the size of the pipe is the inside diameter of the pipe. Is that always the case? No, I mean, every kind of pipe has a different inside diameter. I mean, it's, you could come up with lots of these charts for ductile iron pipe and PVC and for concrete and copper and whatever. I mean, they'd all be different, right? But this is in the ballpark. And that is something I think it's important to understand about hydraulic calculations, is they're in the ballpark too. When I'm doing this stuff, I don't expect to get an exact right on the dot answer. You know, this stuff, there's too much variation in pipe sizes and actual elevations and all this kind of stuff. You know, this stuff isn't an exact science, I don't think. Especially what we're about to look at, which is head loss, okay? But I do want to make you aware that you've got this chart available to you. Now, it won't work for every case. I mean, if someone for some reason has 9-inch pipe, this isn't going to get it for you. But all the same, it's, for the commonly available pipe sizes and municipal type stuff, and for the common flow rates you push to those pipes, it does have the velocities. It can save you a lot of work. Okay? Other thing you can do is just make a spreadsheet for that. If you have pipes, you can, but whatever, you've got it right there on a chart. So let's look. I just want to make you aware of that. Now let's look at head loss a little bit, okay? Why don't we do that? We got a few minutes. So why don't we start in on this? All right, so far that's a number that I've just been giving you. Now what head loss is it's energy loss that goes out of the flow, that goes out of the water when it moves. So head loss occurs whenever the water moves. Okay. And there's different ways to calculate it. But first let's look a little bit at what it is. Okay, it's energy loss is what it is. And I don't know if this is on, I'm missing a couple pages out of my book, so I'm a little bit unsure where I might have this stuff got up on my slide. I don't know. 107, is it? Okay, thanks. Okay, so head loss occurs only when the water flows. If it's not flowing, there's no head loss. So I think of head loss as occurring with friction and turbulence. What happens is you get a little bit of heat in the water and it just dissipates off into the atmosphere and you've lost the energy. Okay, there's two kinds. There's major head loss, which is head loss in straight pipes, and then minor head loss, which is head loss in fittings. Okay. Now, head loss, there's a few things to know about it. If your pipe gets rougher, or if your pipe gets longer, and when your velocity of flow goes up, you get more head loss. Okay, so a rough pipe, a long pipe, a high flow rate, and a low pipe size will get you more head loss. Head loss seems to be independent of pressure. It doesn't really depend on that at all. It's just basically velocity and what the speed of the water is moving through the pipe. Okay, and those things are pretty intuitive, I think. Obviously, a rough pipe, you'll get more friction. Longer pipe, you got more head loss that builds up over the length. And high velocity gets you more turbulent, rougher flow, which gets you more friction. So high velocity occurs because what you're doing here, you're using V equals Q over A. So if you push more flow rate through, you get higher velocity, that's Q. And if your A goes down, you get higher velocity, okay? Now there's two ways to calculate this. There's equations, and then the equations have been put onto charts also. These methods were created roughly 100 years ago. Two methods. They're named after the people that developed them. In both cases, they were two people working together. So Hayes and Williams came up with a method that's easier, but it's less accurate. And Darcy Weisbach came up with a method that's harder, but more accurate. Okay. So let's start with the hard one. Normally I start with the easy one, but you guys are such a smart class. I figure I should start with the hard one. It just seems like the right thing to do. Okay. So this is actually later in the chapter. It's on page 118. So what's going on here are these people go off into the lab and they try and develop a formula that will express head loss, which is a pretty hard thing to do. I mean, you get so many variables in head loss and pipe sizes and all that. I'm not pretty amazed that these people were able to do this. Okay. So Darcy and Weisbach looked at this in a real theoretical way. And they say head loss should depend on the long pipe, So the longer it is, the more head loss. So L goes on the top. It should depend on the velocity head, which is v squared over 2g. The higher the velocity head, the more the head loss. Keep in mind that g is gravity, and that's 32.2. And then head loss should also depend on the diameter of the pipe. The bigger the pipe, the less the head loss, so that goes on the bottom. Okay. Now all these things are in feet, which it might be a little odd, but so the one thing there, you got to get diameter in feet. And then they also have a friction factor, which describes how rough the pipe is on the inside. That affects the flow going through. Okay. So there's the formula. Now the hard thing is to come up with this F, okay? Now first thing is there's two kinds of flow. There's laminar and turbulent. Laminar is nice, smooth, easy flow. The water doesn't jump around a lot. Laminar is like flow in a channel, in a lined channel. Okay, like maybe the irrigation channels for Los Angeles or something like that. Turbulent is the more normal condition. It's when the flow's jumping around and moving around like a mountain river or something like that. Okay? And someone actually came up with a number to determine whether flow is going to be laminar, which is smooth, or turbulent, which is rough, called the Reynolds number. And that's the pipe diameter in feet, the velocity in feet per second, the density of the fluid, and the absolute viscosity. Okay, so that's called the Reynolds number. And if the Reynolds number is more than 2100, the flow becomes turbulent. And if it's less than 2100, it's not turbulent. Okay. Now to find this thing, we got to find F, and that's the hard thing to do here. We got to find the relative roughness. So you'd actually have to look at the inside of the pipe and find the depth of the biggest imperfection on the pipe, the biggest pit or the biggest nodule on there. And then you divide that by the pipe diameter. So relative roughness is that biggest imperfection divided by the pipe diameter. So if you have this relative roughness, and if you have the Reynolds number, there's a chart where you can find F called the Moody Diagram, okay? I think the normal thing to say there is people generally get kind of moody when they look at this because there's so many lines on it, it looks complicated. But it's okay, all right? So there's the Moody diagram. It's on page 120. All right, let's say we've got water that's at 70 degrees Fahrenheit. Your book might say 60, but the temperature is 70. So if it does say 60, change it to 70. Okay. And let's go have a look at page 58 and find the viscosity and the density. And that should be on page 58. You've got a table in there that should give that to you. So we're at 70 degrees. And what do we got here? We want the density, which is 1.936. Now this is the actual density, okay? So the density is 1.936 slugs per cubic foot, okay? And then the viscosity, which is how sticky the water is 1, 2, 3, 4 zeros and a 203. Okay. So we look both of those up on this chart. And that's in pounds second per square foot. Okay. And this is slug second. Slug, that should just be slug per cubic foot. We got a little typo there. So you look those up, and then you do the Reynolds number. Okay, so what the Reynolds number is, yeah, we do. So the Reynolds number, and I'm sorry, I kind of lost this. And that's not one I've got in my memory. There we go. Now we're getting there. Okay, the Reynolds number, and I've got the formula down there. It's D. Now D is 6 inches in the problem statement. Okay. But we got to be in feet, so that's half a foot. 6 inches is half a foot. Okay, now we got to get the velocity. Now this is where that chart will come in handy that I was showing you a little earlier. We got 6-inch pipe and 600 gallons per minute. So what we can do is go to that head loss chart on page 108 and have a look at 6-inch pipe and 600 gallons per minute, and it looks like the velocity is 6.81 feet per second. Okay. So that saves an awful lot of work to have that chart in a situation like that. Then we multiply it by the density, 1.936 slugs per cubic foot. And we divide it by the viscosity. Okay, that's pounds second per foot squared. And what we get for the Reynolds number is 325 times 10 to the 5th when you do that. So there you go. Okay, and I think we're about out of time. And I can see you guys are getting overexcited about this, so we'll yeah, there we go. Yeah. Now we'll go over this. Now I will get you a little bit more straightforward way to do this too. So don't, I just want to show you this once, okay? All right, so call it good. Hope everyone has a good weekend. I don't know if the weather's going to stay this way or not. I hope it will. Sure is a nice day.